Hi, everyone. I'm JJ. Welcome to this course. Today, I'm going to talk about how multimodal AI empowers people. I'm currently a professor at Tsinghua University and also a PI. I'm working at the Institute for AI Industry Research. We call it AIR. I will talk about our current research investments at AIR later on. I think I'll just briefly go through my previous experience. I got my PhD degree about 10 years ago from MIT. My focus area was spoken dialogue systems like Siri. So I worked on speech recognition, natural language processing, and dialogue policy learning. And after graduation, I stayed at MIT for a couple of years, and I worked as a research scientist. I continued working on spoken dialogue systems. And then after a couple of years, I joined Microsoft Research, or MSR, as a researcher. At Microsoft, I worked on NLP and question answering in particular, and also dialogue, of course. Then a couple of years later, I had a change of heart. I was interested in investment and entrepreneurship. So I quit Microsoft and I went to University of Cambridge and I did an MBA. So it was a 1-year program. And after that, I joined a startup in China. I was the director of product at the company for a little while. And then in 2016, I went back to the US and I rejoined MSR as a principal research manager. And I was leading a multimodal AI research group. And I had around a dozen researchers working with me. And also every year we had around a dozen PhD interns working with us on many different topics in multimodal AI. So today I'm going to talk about some of the interesting projects that we've been working on and how that can empower people and can bring benefits to our society. And earlier this year, I joined Tsinghua University in China. Currently, I'm at AIR, Institute for AI Industry Research. AIR is a new model for university and enterprise collaboration. Here, we want to develop the latest core AI technologies for breakthroughs that can empower different industries, such as transportation or IoT and healthcare and so on. And another goal that we have is talent development. So we want to cultivate students that not only have strong technical background, but also has a good view in industry and also with social conscience. And we also serve as a think tank to help our partner industry companies to formulate industrial strategies and business models that AI could contribute to. And our hope is that we could also bring some thought leadership in all the different industries that we work in to help set some industrial standards and also bring the latest technologies that could power many different applications. And I will talk about the detailed areas that we invest in later on. Okay, so now let's have a look at the AI evolution. AI has gone through a few ups and downs in the past, I would say, 7 decades. In the 1950s, Alan Turing asked the question, can machines think? Which led to the Turing test, which validates whether a machine has a human-like intelligence. And in the mid-1950s, the concept of AI was introduced with the birth of a perceptron, and which inspired the first wave of AI research. However, in the 1970s, and tell the user what an image or a video is about, I will explain that later on. And another example is the prototype of AI glass. It combines glasses with sound sensors and GPS technologies, which can give spoken directions to the user and recognize, say, currency or read signs or identify colors, among other things. It's like an assistant in your ears. And it also employs machine learning technologies to recognize different places and objects because it uses ultrasound sensors, so it can also detect, say, translucent obstacles like a glass door, so you don't run into a door. Another interesting example is a finger reader developed by MIT Media Labs. This application can help vision impaired people to read books just with their fingers. So all these applications rely on multimodal AI technology. So what is multimodal AI? You can consider an AI system as a human brain. And the goal is to build models that could take in multimodal signals, such as speech, text, image, and video, and process all these signals jointly to perform intelligent tasks such as inference, prediction, and decision-making. Okay, so here we touch on the first principle of sustainable AI, responsive, meaning that our technology should be able to handle multimodality signals from the real world to perform diverse tasks that could help people. I guess it's fair to say that deep learning has revolutionized the AI world. Prior deep learning, the speech community, NLP community, and vision communities were all separated. And each community focused on domain-specific problems, such as speech recognition or image classification. Deep learning shifted the AI field from single modality study to multimodality integration. So instead of using diverse symbolic spaces for speech waveforms or text tokens or image pixels, now everything is encoded in the universal neural space, which heralds the advent of multimodal fusion in the new age of AI. I'll give you some examples of multimodal tasks. So in multimodal tasks, the input and output of a system can be multimodal signals, such as text or image or speech or video. So if both the input and the output are text, then it's machine translation. It's a single modality task from one language to another. If the input and output are both images, then it's an image translation task from a color image to, say, a blurred image or a black and white image. If the input is the image and the output is text, then it is an image captioning task. So given an image, the model will generate a natural language description of the image. So there's a dog sitting on the carpet. And if the input is text and the output is image, then it's a text-to-image synthesis. Given a description, the model is able to create a new image that fits the description. And there are also other tasks that take both images and text as input. For example, in visual QA task, given an image and a question regarding the image, the model can generate a textual answer based on the visual content in the image and to answer the question. And if it's a multi-turn setting, then it's visual dialogue, meaning multi-turn of visual QA. Another interesting example is language-based image editing. So given an initial sketch and a textual description, we can build an agent that edits the image into a new design following the description from the user. And if we turn this into multi-turn, then the problem can be formulated as interactive image editing through dialogue. And beyond that, we also have visual reasoning and visual entailment tasks where the models take in both image and text as input and do multimodal reasoning and inference to interpret the visual content, such as the popular VCR visual content reasoning task. Image text retrieval is another task that has high value in practical applications. We're given a text query, the system searches for the most relevant images to the query, or vice versa. And this is not a comprehensive list. There's also visual grounding, visual language navigation, and other interesting tasks. And that's just in the realm of images. If we consider video, then there are also tasks like video captioning, video synthesis, video QA, entailment, and video moment retrieval. So this is a very diversified area with a lot of interesting research going on. Okay, so now I want to show you a quick demo just to show what kind of real applications that could be built with all these tasks and technologies that I just mentioned earlier on. And so we built two chatbots. One is for visual question answering. The other is for dialogue-based image editing. So the first one, the user could type some questions. They could upload the image and ask questions, and the bot could chat with the user and answer questions regarding the images. And then the second bot, the user can design some products by talking to the bot, and the bot will play as an assistant, following the instructions of the user. The bot can generate some new images or modify previous designs. So let's have a look at the video. So this is the first bot which can answer questions regarding the particular image. And the user is asking some questions about this. Now the user is uploading a different image. And the user asks what's the skill limit. It's a very small size of the red bottom. And this is the second bot. The user wants to design a t-shirt. And now make it black. Now the bot will interpret, okay, it's black, but change the color. And until this is what the bot proposed. Now the user switch to women's shirt. Now they want pink. So the color was changed to pink. And make it white with short sleeves. Okay. Now it seems bot changed it to a white shirt with short sleeves. So I hope you got all caught the conversations between the user and the bot. So these are just some fun prototypes that we use. And many of these applications could eventually be plugged into applications for like vision impaired people, such like the CAA or other similar products. Okay, so now we'll do the fun part, the technical part. So how do we make it happen? In machine learning, there's supervised learning with label data, and unsupervised learning with unlabeled data. And there's also semi-supervised learning somewhere in between. Supervised learning means that you give the machine some images to learn, and you provide the labels for each image. For example, if we're building an image classification model, then we give the model tons of images, and we tell the model which image is a duck, which image is not a duck. And then the model can learn from all those images to identify, given a new image, whether it's a duck or not. And unsupervised learning means that the computer has to learn from unlabeled data. So we also give the model tons of images, but we don't tell the model whether this image is a duck or not. And the model has to learn on itself. But most data in the real world have no labels, and it's expensive and time-consuming to hire human annotators to label a large amount of data. So self-supervised learning comes to rescue. So the main idea is that beyond explicit labels, unlabeled raw data themselves also have some intrinsic supervision signals for model training. So by manipulating images, for example, such as turning color images to black and white, or carving out a region from the image, or scrambling the positions of different regions, we call it jigsaw puzzles, we could train a neural network with these artificial modifications as free labels. So the key concept of self-supervised learning is to train the model with the data itself, but with some artificial labels. And that was in the computer vision domain. In the NLP field, natural language processing, we also witnessed a breakthrough with self-supervised learning approaches, such as BERT model and GPT-3. Both models use transformer. So transformer is a very cool and powerful model architecture that is ubiquitous nowadays in deep learning. So these models could train large-scale encoder-decoder with free text from Wikipedia or News Quora. So it's a lot of data to use without labels. And now we're going into multimodal. The traditional way of machine learning is to handcraft and customize single model for each specific task, such as a VQA and VCR, ALVR, GQA, and so on. And different models for different tasks look very different in architecture and feature design. So in the new age of computing, instead of designing many task-specific models, here we can use self-supervised learning to train one large-scale task-agnostic model instead, meaning that this universal model is task-independent and can be customized for different tasks during downstream fine-tuning. We call it downstream fine-tuning, meaning that given a pre-trained model, we use the transfer learning approach to adapt the model to different domain. So we call this the pre-training method, which can handle large-scale data and diverse tasks in a generic and efficient way. So the wave of image text pre-training started in the summer of 2019 with large-scale models such as ViewBERT, LexBERT, United leading the way. So United was a model that our team built when I was still at Microsoft. Since then, many more models have been proposed utilizing different features and different pre-training tasks. Another stream of work is video plus text pre-training, which enjoys a parallel growth as image plus text pre-training. This field has advanced a lot from early work by Google and institutes in Europe in 2019 to the latest Multimodal and December. So I mentioned earlier that we use self-supervised learning to do model pre-training. And so here are some common data sets that people use for pre-training, such as COCO captions and visual genome. Each data set consists of many image text pairs. And the text is a description of the visual content in the image, so they're associated pairs. Then we design some pre-training tasks to train the model. Take United as an example. On the high level, United is built with one stream architecture over transformer. Given a dataset with image text pairs, we first use an image embedder with fast RCN to extract some region features of the image. Then we use a text embedder to extract some word tokens features from text. You can consider this as data pre-processing for images and for text. Then we use the transformer to pre-train the model with well-designed pre-training tasks, such as masked language modeling or masked region modeling or image text matching. For example, in masked region modeling, you mask out a region in the image, and then you train the model to predict the original region in that image. So the goal of model pre-training is to learn the multimodal alignment between different modalities. Here's an example of a text-image attention with the alignment on image-text pairs learned from the model. So here are two examples. As you can see in the top example, the model learns to attend to specific regions in the image to associate with different objects described in the text. For example, from the girl to the shirt, to sitting, and to bicycle. So you can see the attention moves. So that's the alignment between the image regions and the words in the sentence. And the bottom one shows attention to the man, the child, and then the puzzle. So this is how the model learns all this alignment between different modalities. And after pre-training, we can apply the model to diverse downstream tasks using transfer learning. Here I just listed a few applications such as visual QA, where the system can answer a question given an image, like what colors are her eyes, and the model can answer the question after reading this image. Or visual entailment, where given an image and a hypothesis about the visual content, the model predicts whether this hypothesis, say two women are holding packages, entails or contradicts the image. Or reforming expressions is another good example, where given an image and a description about a particular region in the image, like the woman washing dishes, and the model could find the right region corresponding to that description. So these are just some typical downstream tasks. And for video plus text tasks, it's a similar process. We can pre-train the model with a video plus text datasets, such as how to 100M dataset, which consists of 100 million YouTube videos. And downstream tasks include action recognition from videos, or video retrieval, video captioning, and video QA. Okay, just to summarize, there's a wide range of research topics in vision and language pre-training, such as training strategies, end-to-end pre-training, model robustness, and model efficiency, and other topics like multilingual applications and probing analysis, and so on. So the probing analysis we did was to understand the black box of pre-trained model, because many deep learning models that we train are kind of black box. So you don't know what's behind the scene, and you don't know what do the tricks. So I think this is also another interesting area, explainable AI, that could help people understand how AI works. So if you'd like to learn more about this field, together with my Microsoft colleagues, we gave a tutorial on vision and language research at CVPR last year. So you can find all the recorded videos and slides on the tutorial website. So we cover topics such as visual captioning, visual QA, reasoning, text-image synthesis, and self-supervised learning. So you can find all the details there. And last month, we hosted another tutorial at CVPR this year, together with my colleagues at Microsoft, Google, and UCSC, and other institutes. So this time, we introduced the latest development in this field, from vision language pre-training to vision language navigation, which is also a very interesting area. So you can find all the recorded videos on the tutorial website as well. Another useful resource is datasets. Recently, we just released a new benchmark, we call it Value, for video and language understanding evaluation. This benchmark includes 11 different video and language understanding tasks, from video retrieval to video QA and video captioning. You can download all the datasets and participate in our challenge by submitting to the leaderboard. You can also download the code base to play with the baseline models. So this is a great way to get your hands dirty and play with some existing code, and also develop some new algorithms. And you could also use some existing pre-trained models, just do some fine-tuning as new tasks, and to see how that works. Okay, so that was some high-level overview of multimodal AI research areas. So here comes the other two pillars of sustainable AI. Responsible, meaning that AI technology can help protect the environment by saving energy and ensuring human safety. And resilient, meaning that we can use AI techs to build robust and secure systems for the benefits of people and society, while maintaining data privacy, which is very important. So now I'm switching gear to talk about the work that we're doing at Tsinghua Air. AIR stands for AI Industry Research, and our focus is to develop new AI technologies and how to apply the new techs to transform diverse industries. And the three pillars of investment at AIR include AI plus transportation, AI plus IoT, and AI plus healthcare. Now we have a ABCD focus proposed by Yaqing. A means AI, B means big data. We could get a lot of data from our industrial partners to do research. C means cloud computing, edge computing, and D means device. So now let's zoom in on transportation as an example. In this new age, the technical shift is overwhelming in this field. Now the industry is growing towards more electrified, connected, autonomous, and sharing, with the development of self-driving cars and Internet of Things, all the cool things. So why do we need autonomous driving at first place? And what's the future of self-driving vehicles? Statistics show that over 90% of road accidents are caused by human error. So we hope that with technology, we can help people make precise decisions, and so we can lift the safety bar and compensate for human errors. Another gain is efficiency. We all dream of the day when we can all just sit back and relax in our vehicles in our daily commute. And we could work on other things, hopefully not conferencing, but we could enjoy other leisure activities while the car just drives itself to the destination. And also it's a huge market, economically speaking. A passenger car alone with autonomous driving capabilities can generate 1.5 trillion US dollars per year. So with all this motivation, I think people have spent a lot of effort investigating this area in the past 40 years. So the quest started when DARPA launched the ALV challenge, the Autonomous Land Vehicle Project. And 20 years later, the DARPA Autonomous Driving Challenge revived the investigation and made autonomous driving a feasible dream for us. Then started the blossoming of parallel research in the industry, such as Google, Baidu, and Waymo. And now it has been commercialized across the globe. Here are some examples of autonomous driving vehicles that have been put into practical use. The first is autonomous driving lorry, which can reduce the cost of long-haul transportation significantly. And also it could save a lot of human effort. The second application is on-campus logistics. This tiny model has been deployed in 15 universities in 11 cities, serving over 300K students for fixed route deliveries for logistics. And here's another useful scenario, mine trucks, which usually travel a long distance with heavy load along predefined routes. And these trucks have traveled over 20 million kilometers since 10 years ago, saving significant human cost and human error. So how does AI enable all these autonomous driving vehicles? Here's a simplified framework of different components required for autonomous driving system, including sensors, LiDAR, cameras to capture multimodal signals as raw data on the left side. Then we have computer vision models such as object detection and semantic segmentation to analyze the raw data. Multimodal fusion is also needed here to aggregate different signals from different modalities. And based on this perception layer, we need AI models to help us understand dynamic scenes on the road and topology of the road. Then we can use reinforcement learning and other AI algorithms to enable end-to-end planning and continuous decision-making. So AI is everywhere. Behind the scene, there are many AI technologies that can power this complicated framework for autonomous driving, such as perception, planning, simulation, human-machine interaction, system safety, and so on. I guess it's fair to say that autonomous driving is one of the most difficult and narrow AI problems, and it's also a bounded problem. Here are just some examples of typical AI tasks that we are investigating at AIR, such as 3D object detection and semantic segmentation to understand the dynamic and complex scenes on the road. Another important task is multimodal fusion, how to train an AI model to fuse different signals from different modalities, from different sensors, such as cameras and LiDAR. Model compression and data compression are also critical edge computing technologies that will enable easy deployment of compressed models on end devices, where computational resources are limited. We also need a simulation environment to train different models before deploying them in the real scenarios, because the cost is really high. Here's a visualization of the semantic segmentation task. Given a video clip, the model can detect different objects in the visual scene and track the objects in sequential video frames. This helps us understand the dynamic scene transitions on the road. Multimodal fusion, we just discussed in the first half of the session when we talk about video plus text and image plus text fusion. Here, the setting is a bit different. Instead of text, we replace the input signals with camera and LiDAR signals. But as you can see, the model architecture looks really familiar, right? When we talk about vision and language pre-training, we use transformers to fuse the multimodality signals. Here, we can apply the same framework to fuse, say, RGB images and LiDAR signals using transformers. Here's some more details about model compression. When we worked on vision and language between models, we also encountered the problem of super large models, which takes a long time to train and requires a large amount of GPU resources. Back then, we tried different methods such as knowledge distillation or KD to compress a large model into a small one, such as a 24-layer model into a 12-layer model or 6 layers. And the strategy is to use a large model as a teacher and distill the learned knowledge from the teacher model to a smaller student model. This can be applied to different models in the autonomous driving framework as well, which ensures real-time computation on end devices when fog computing is not available. Okay, so I briefly discussed some key research topics in multimodal AI and how it can empower people along the 3 sustainable dimensions: responsive, responsible, and resilient. Our hope is that with this sustainable development goals as guideline, our AI technology can best contribute to the human society while minimizing the negative impact on environment and on human safety and privacy, while making contributions to many different applications and different industries to empower people. Okay, that's all.